So hello everyone, I'm Krishna Kumar, working as a research fellow in the Department of Electrical, Computer and Software Engineering at the University of Auckland, New Zealand. So it's a pleasure to connect with all of you today and talk about modern digital substations from process level to control center integration. So the first question would be, why digital? So as we move towards digital substations and digital technologies, the advantages become very clear. Digital solutions offer up to 30% faster delivery and lead time, and installation plus commissioning time can be also reduced about 25%. This means project can go live quicker and with fewer delays. And also the digital architectures are modular and scalable, so expanding or modifying the system becomes much easier without major redesign. We also gain higher accuracy, ensuring consistent performance across the entire system. Also, the digital signals can, enable easy and efficient transmission without the limitation and noise issues associated with the copper wiring. On the safety front, digital systems use very low energy fiber optic signals, which significantly increase safety, especially in a high voltage environment. Also, digital technology requires up to 10% less space, helping optimize substation layouts. So this leads to increased reliability and availability, ensuring the system performance better and with fewer failures. So digital switchgear, what is it? So digital switchgear is a key enabler for smart electric networks. It combines the latest digital technologies with modern switchgear design to provide greater flexibility, higher reliability, and enhanced safety, while reducing weight, physical footprint, and overall delivery time. And one of the major strengths is seamless integration. So digital switchgear brings together protection, control, sensing devices into one unified system. And all the measurement status information and control commands are transferred through a real-time Ethernet communication bus. And the most of the very popular the IC standard is the 61850 protocol. This enables large bundles of copper wires and simplify the entire communication structure. Digital switchgear also enables proactive management throughout its entire life cycle, as all data flows digitally, so it supports smart functionalities such as real-time diagnostic, power management, health monitoring, and remote supervision. One of the biggest advantages of digital switchgear is the significant improvement in safety. So unlike traditional metering transformers, these sensors operate at very low energy levels, meaning the risk to workers is going to be reduced. And when testing or handling secondary circuits, technicians are no longer exposed to high voltage conditions. And because less material is exposed to the high voltage electrical stress, the equipment itself experiences fewer failure, contributing to safer long-term operation. So the digital switchgear significantly reduces energy losses by using advanced sensors. It also cuts down on the resources needed during manufacturing, which reduces overall environmental impact. So if we look at a typical installation of 14 digital switchgear panels over a 30-year operating period, the benefits become very clear. So we can reduce energy consumption by up to 250 megawatt hour. In terms of emissions, this translates to saving of up to 150 tons of CO2. That equivalent to the emission from driving a mid-sized car for 1.25 million kilometers. And to absorb that much CO2, naturally we would need 8,200 trees working for an entire year. Another major benefit of digital switchgear is the increase in flexibility. As network requirements change, such as variation in feeder current, you can easily adapt the switchgear without any physical modification. And most changes can be made just by modifying parameters or logic inside the protection relay. There is no need to replace hardware components, which saves time and cost, right? And because the system is built on the IC 61850 standard, it remains future-proof, right? So this ensures that any future updates or extensions can be integrated efficiently and seamlessly. So another important advantage of digital switchgear is the reduced physical footprint. Compared to the conventional medium voltage switchgear, digital switchgear can reduce the footprint by 10%, right? So this is possible because certain cubicle, such as bus bar metering cubicle, can often be removed. Voltage sensors and other digital components take up for less space than traditional metering equipment, right? So with digital switchgear, delivery can be up to 30% faster. This means a short time for ordering to actual operation, right? So there are several reasons behind this improvement. For sensor technology, which enables a one size fit all approach, unlike traditional CTs and VTs that are needed more engineering customization. And the second is the sensors have a wider operating range. So the same sensors can be used for many different applications, which reducing design and procurement delays. Third could be these sensors are typically available in stock and then eliminating long lead times. And the last could be the hardware wiring. As the hardware wiring becomes minimal, so most configuration can be handled through software, which speeds up the installation and commissioning, right? So this improvement is driven largely by the use of IEC 61850 communication, uh, which is a global standard for substation communication. In traditional switchgear design, we need a large number of wires running between cubicles to exchange signals. So this is not only makes the system complex, but also increases installation time and failure points. With digital switchgear, all the information is transmitted through a self-supervised communication cable, right? So this drastically simplifies the interconnection between cubicles. Uh, it also gives us tremendous flexibility, so we can adapt or modify the switchgear without requiring physical rewiring or hardware changes. In IC 61850s, GOOSE messaging allows high-speed peer-to-peer communication among devices. This reduces cabling even further while improving response time, right? So if you look at the before picture on the left, you can see what traditional copper-based wire looks like. There are hundreds of cables coming down from the cable tray. Each signal needs its own copper wire, which means more material, more labor, and more opportunities for mistakes or failures. Now compare that to the after picture on the right. Here the cables tray is completely gone. Instead of large bundles of copper wires, we have a single clean conduit carrying fiber optic cables, right? On the left side, we have a modern digital protection and control cabinet. This integrates multiple relays and control units into one compact platform, reducing complexity, minimizing wiring, and improving overall efficiency. Now shift to the bottom center. Uh, Traditional substation still depends heavily on extensive copper wiring for relays, circuit breakers, and RTUs, CTs, PTs, uh, so which increases uh, system complexity, and this creates a system that are harder to maintain, more prone to errors, and far less flexible. In contrast, at the top center, we see a digital substation. Here, fiber optic connections, intelligent electronic devices, and self-healing network simplifying wiring, provide continuous supervision, and significantly enhance its reliability, right? Finally, on the top right, notice how optical fiber replace massive copper cables, resulting in cleaner, safer, and far more maintainable installations. Evolution of substation automation. So let's start with the first generation, uh, that is 1960s. Back then, everything was hardwired. Serial communication and parallel wiring dominated. Control centers had a simple HMI and MIMIC boards. Protection and control wires performed uh, by hardwire RTUs and relays. The downside was obvious, lots of copper wires, high cost, and very little flexibility. Changes are very slow and expensive. In the second generation, around 1985, we moved to point-to-point communications. Uh, Station gained a better, the controllers and HMIs, and communications improved. However, each device still required its own physical connections, so scalability remained limited. So in the third generation, about 2004, introduced the game change, IC 61850, and the station bus using Ethernet. So intelligent devices, we call it in short, we call it IEDs, begin to talk to each other over a common network. This reduced wiring, improved interoperability across vendors, and dramatically speed up data exchange for protection and control. So we still had a parallel wiring to the process equipment, but the station level digitization was a major leap. And finally, today's fourth generation, the fully digital substation, this adds the IC 61850 process bus merging unit that digitize CT and VT signals and full band and IoT integration, right? So now simple value and fast messages like GOOSE, flow over the internet, protection, control, assessment management, and analytics can all be done remotely and in real time. The results for less copper, faster protection, and a platform of predictive maintenance and advanced grid services. So in short, we moved from lots of hard wiring to point communication and then to a digital station bus and now to a digital process bus with IoT and analytics. So each step reduced complexity, improved speed, and enabled richer monitoring and control, right? So the practical benefits are lower installation cost, faster fault detection, vendor interoperability, and the ability to apply analytics for health monitoring and predictive maintenance. So now comparing two types of IEC 6150 based digital substations. One is a decentralized digital substation on the left hand, and at the right hand we have centralized substation protection. We call it in short like CSPACS. It's a centralized substation protection, automation, and control system. The IC 61850 based decentralized digital substation uses multiple intelligence devices, that is IEDs, each performing specific protection, control, and monitoring tasks. At the top of control center or gateway and HMI manage overall substation operations and provide the human-machine interface for operators, right? The IEDs connect to the substation bus and communicate with the control center. Field devices such as circuit breakers, transformers, and sensors are connected to protection and instrumentation devices. In short, we call it PIDs, which in turn communicate digitally via the process bus to the IEDs. In this step, data flow from field device to PIDs, then IEDs, and finally to the control center. While this centralized structure offers flexibility, it increases complexity because each IED must be individually configured and maintained. On the other hand, the centralized substation protection digital substation replaces multiple IEDs with a single centralized platform. Right? The control center or gateway and HMI operates similarly, connecting to the central substation, centralized substation, to manage operations and provide visualizations. Field devices still interface through PIDs, but all protection, control, and metering functions are centralized within the CS packs. This centralized reduces hardware complexity, simplifies maintenance and configurations, and improves interoperability with other digital substation systems. Compared to the decentralized approaches, CS packs offers lower complexity, higher scalability, easier maintenance, and potentially lower cost. Right? Now the centralized versus virtualized protection. So this image shows how substation protection has evolved from hardware-based devices to software-based virtual systems. In conventional protection, each feeder, transformer, generator, or motor has its own dedicated protection relay, meaning many separate devices, wiring, and hardware components. In centralized protection, it replaces, these multiple relays with one central unit that runs several protection applications on a single piece of hardware, reducing equipment and simplifying maintenance, right? The most modern approach is virtualized protection, where protection functions run as a virtual machine or software application on a shared computing platform. This decouples software from hardware, allows multiple protection functions to run on one industrial server, and provides higher flexibility, scalability, and easier updates. Architecture redundancy considerations. So a digital substation improves reliability and availability by using multiple layers of redundancy. This diagram shows how this redundancy is introduced at different level of the system. First, redundant sensors and redundant merging units ensures that voltage and current measurements continue even if one sensor or merging unit fails. These merging units publish sample values on two separate process buses, providing duplicated measurement data paths. Next, the substation includes redundant intelligent electronic devices, shown as a protection A main and protection B backup relays. If one IEDs fail, the second takes over without interrupting protection functions. The communication network itself is also fully redundant. The system uses parallel redundancy protocol, that is a PRP, on both the process bus and station bus, ensuring that every message is sent simultaneously on two independent networks. This guarantees zero-time recovery if a communication link fails. Devices such as GOOSE, A-B publishers, merging units, protection relays, and the switch at the boundary between the process bus and the station bus all participate in this redundant communication architecture. Messages like GOOSE and MMS are transmitted through both A and B network, so the control, monitoring, and protection functions always receives reliable data, right? So the sample value considerations, isolation, and testing. So this diagram explains how an intelligent device behaves when it is placed in simulation mode. In this mode, the relay is prepared to accept only the simulation sample value uh, for testing purposes. This prevents the device from reacting to a real process measurement while engineers perform functional or system testing. So the two types of sample value sources are shown. The first one is MU1 process, which represent the real merging unit sending actual electrical measurement from the power system. These real sample values frames carry a flag SVSIM equal to false, meaning they are real live data. The second source is MU1 simulator, which sends artificial SV frame for testing. These frames are marked SVSIM when it's true, indicating that they are simulated data intended for testing the IEDs. When the IED is set to sim true, it will ignore all sample values frame that come from the real process until because those frames are not marked as simulation. In other words, the IEDs blocks any data with SVSIM false. At the same time, it accepts only the SV frame with SVSIM true coming from the simulator. This ensures that during the testing procedures, only the simulated test values influence the relay's internal protection functions, right? So IC 61850 is an international standard designed to simplify, unify, and improve communication within electrical substations. Right? So it provides a common framework that allows devices from different manufacturers to communicate seamlessly, ensuring interoperability and reducing engineering complexities. The standard supports detailed modeling of substations, covering both primary equipment such as transformers, circuit breakers, and disconnectors, and the secondary equipment including protection relays, control units, and communication devices. By representing all the components in a structured, object-oriented format, IC 6150 enables consistent data exchange and efficient system integration. One of the core elements of IC 61850 is that it defines communication between devices in a substation. Instead of relying on a traditional hardwiring, the standard uses high-speed Ethernet-based communication protocols. So this facilitates faster protection signals, reliable control commands, and real-time monitoring, ultimately improving the performance and safety of the entire substation. Also, IC 61850 includes a well-defined engineering process and methodology for implementing substation automation functions. It guides engineers through system design, configuration testing, and maintenance using standardized tools such as SCL, Substation Configuration Language. This structured methodology reduces human error, saves time, ensures consistent results. The standards uses a modular and scalable approach, allowing systems to be expanded, upgraded, or modified without compromising existing functionalities. This flexibility makes IC 61850 highly future-proof, enabling utilities to adopt emerging technologies and integrate new devices with minimal efforts. Beyond electrical substation, IC 61850 is also applicable to broader automation areas, including industrial facilities, renewable energy plants, and distributed generation systems. Its robust communications features makes this ideal for modern smart grid application, where interoperability, speed, and reliability are essential, right? So this diagram shows the overall structure of the IC 61850 standard, which defines communication and data modeling for modern electrical substations. At the top, IC 61851 and IC 61852 provides the introduction and glossary, uh, forming the foundation for understanding the rest of the standard. The next group indicates general requirements, IC 61853, and system project management guidelines, which is IC 61854, which describes how systems should be planned, engineering, and managed. The communication requirement for devices and functions are covered in IEC 61855, and the fundamental principle and the modern models are defined in IEC 61857-1. The core of the standard lies in the IEC 61857 series, which defines data models and logical nodes. These includes basic models and abstract services, common data classes, and logical node classes. Additional application guides, that is 61857-5 and 7-5XX, and domain-specific models, IC 61857-4, extend these concepts. For system configuration, IC 61856 defines the substation configuration language, that is SCL. Technical reports and guideline under IC 61850-90 provides further clarification and advanced use cases. Communication mappings to actual network protocol are provided in IC 61850 Chapter 8 for general messages and IC 61859 for sample values. This mapping supports real-world implementation for the standard in device and networks, right? So the next one is IC 61850 protocol suite. The diagram represents the communication architecture of the IC 61850 standard, which is used in modern digital substation to ensure reliable, fast, and standardized data exchange. At the higher level, in the data model, I mean data and services, which defines what types of information are exchanged and how they are structured. So this includes four key services types, which is client server, that is MMS suite, manufacturing message specifications for monitoring, control, and reporting, time sync, we call it SNTP, for synchronizing all devices in the substation, GOOSE, which supports rapid peer-to-peer messaging for protection and interlocking functions, and sample values, in short, we call it SV, which deliver digitized measurements such as voltage and current from merging units. The middle section labeled mapping shows how each type of services is associated with its corresponding communication protocol. MMS traffic is mapped to the MMS protocol, SMTP, uses the SMTP protocol, and both run on over IP networks. However, GOOSE and SV are mapped directly to the Ethernet layer instead of TCP/IP because they require extremely low latency and deterministic delivery for protection applications. So this mapping ensures that each service type is transported in the most efficient way based on the time critical requirements. The lower part of this diagram illustrates the communication stack of each data type. MMS messages travel through the MMS protocol, then through the TCP IP, and finally over the Ethernet. Similarly, SMTP messages travel via UDP, then IP, and then Ethernet. Because Speed and priority are essential for GOOSE and SB. Uh, these masses bypass TCP, UDP, and IP are carried directly over the Ethernet link layer with priority tagging. This tagging ensures that protection-related messages are given priority over the normal traffic. At the bottom, all communication ultimately relies on the Ethernet physical layer, that is IEEE 802.3, typically operating at 100 Mbps speed, right? So this diagram shows the hierarchical data model for IEC 61850 used in the digital substation. At the top is the physical device, an IED, which contains one or more logical devices that groups different functions, such as protection or control. Each logical device includes several logical nodes. These logical nodes contain data objects like breaker position, total active power, uh, which describes functional information. At the lowest level are the data attributes, which hold the actual real-time value exchange during the substation automation. So what is GOOSE messaging? So GOOSE stands for Generic Object Oriented Substation Event. It is a communication method defined under IEC 61850, allowing protection and control IEDs in digital substation to exchange important status information and trip signals quickly and reliably using an Ethernet network. So instead of relying on the traditional hardware copper connection between the relays, breaker, and protection panels, GOOSE enables these signals to be sent directly over the network. This means fewer wires, faster response, and smarter substation. So why GOOSE is important in digital substation? Because it allows us to send fast protection controls like trip, close, interlock, and faulty status within just a few milliseconds. In fact, IEC 61850 requires GOOSE to deliver these messages with an end-to-end delay of less than 4 milliseconds for critical protection functions. Uh, GOOSE also supports peer-to-peer communication among IEDs, enabling devices to interact without needing a centralized control. This leads to systems that are more scalable, easier to maintain, and better prepared for automation and integration for distributed energy resources, right? So another question is, how does interlocking works? So when a fault occurs on the bus bar, the interconnected relays quickly coordinate, causing the relays uh, of the incoming feeder to block the relays of the outgoing feeder and then trip the circuit breaker of the incoming feeder. The same happens vice versa when a fault arises on an outgoing feeder and the relays of the incoming feeder are prohibited to act. Since the GOOSE messages are sent relay to relay through an Ethernet LAN, and thus there is no additional delay for intermediately equipment such as input filters or auxiliary relays, the blocking signals can send faster than in traditional hardwire interlocking scheme. So peer-to-peer communication allows to send blocking signals to all relays at once, making the total operating time independent from the network size, complexity, or topology, right? So in addition to the native security features of interlocking schemes, the operational reliability can be further enhanced by inherent supervision of GOOSE messages. When a blocking circuit is broken, unnecessary tripping is avoided as the blocking is not being issued. So instead of rendering the protection inoperative, in such a case, GOOSE inherent supervision generates an alert to initiate the maintenance repair process and react as quickly as possible. So this supervision function can also be utilized to adapt to application requirement. Depending on the object-to-object protection, one function must often be prioritized over another. For instance, it may be necessary for sacrifice some operational speed in order to achieve selective or vice versa. Such adjustment can be easily made to configure uh, to the configuration of the GOOSE service in order to obtain the best protection possible. So with the ultra fast processing time in RTUs, remote IO extension units can take full advantage of a fast network based on the IEC 61850 GOOSE. So it enables direct and fast communication with relays and master units, and the integration of analog and digital power quality measures at ultra high speed. So the performance class is the highest performance class, I mean the P2 and P3 of the IEC 61850 standards. demanding a total transmission time below the order of a quarter of a cycle. Therefore, setting the limit to 3 milliseconds. The following, the image demonstrate how the transmission time is defined in IC 61850 chapter 5. The trip is the most important fast message in a substation network, and for this reason, the speed performance requirements are particularly high. However, such speed can also be necessary for other operations, including interlocking, intertrip, and logical discrimination between protection functions. Right? So these are the list of references and the companies whose papers and documents were utilized in preparing these slides. So thank you for your attention. I truly appreciate your time and interest, and I look forward to any questions you may have.